When we are dealing with non-accelerating reference frames, in other words, there's no external forces acting on the object, it's just traveling at whatever velocity it maintains, then if it's traveling in a straight line, it's a straight line no matter what. So if I have something traveling in a straight line, if I change the reference frame, that should not change the fact of it being a straight line. The line might look different, but it's not necessarily looking the same. And so therefore, from that, we assume that the transformation between two different reference frames is linear. So if I have some reference frame S here, and I have another reference frame S prime. So S prime is shooting along at some speed V with respect to S. This is the speed of S prime with respect to S, the S frame. Then if it's a linear transformation between the coordinate system, so in the S frame we have the coordinate system of x and t. This is the position, and this is the time. Now we treat this as one-dimensional because if it were three-dimensional, we could always, it's traveling in a straight line, we can always change our coordinate system so that it is traveling in a straight line. So that's the x-axis. And we have another event, so we have the same event happening in the S prime frame at some position x and t with respect to S prime. The relationship between them is x prime is equal to some constant times x plus some constant times time, and t prime is equal to some constant times x plus some constant times time. So if it's a linear relationship, then we should just be able to do some linear transformation. Now, if we have an event happening at the reference frame here, this S prime, so this is the origin in the S prime frame, origin in S prime frame, and this is the origin in the S frame. Then, and this distance right here would be, well, v times t. It's the speed of S prime with respect to S times the amount of time that took place within the S frame. So if it's something that's happening at the origin, we have 0. This is in the S, so the origin is 0 in the S prime frame, is equal to a1x plus a2t. I know that the distance traveled here is vt, so if we actually solve for x here, x is equal to, let's go ahead and put the intermediate step in, negative a1x is equal to a2t, x is equal to negative a2 over a1 times time, and I know that's got to be equal to vt, because if something's happening here from the S's frame, it's a distance vt away. This relationship here implies that time would cancel out, that v is equal to negative a2 over a1. Therefore, a2 over a1 is equal to negative v. We'll exploit that in just a second. We have an invariant. I know that x squared minus c squared t squared equals is a constant, and so I can make that constant anything I want, so I'm going to make that equal to 0. And I know that x prime squared minus c squared t prime squared equals, it has to be the same constant because it's invariant. All right, the reason why this is equal to 0, I know that x squared minus ct squared is equal to some constant. It's not necessarily 0, but I can easily make it 0. And x prime squared minus c squared t prime squared is also equal to the same constant, whatever it happens to be. We'll recognize that time starts whenever I want, as well as I can set my origin wherever I want. So since I can set my origin and I can set time is equal to 0 whenever I want, I'm going to set it up so that this is true. So I'm basically setting the constant. We do something similar with energy, where we establish where potential energy, where we establish where 0 is. So this is a very similar type thing. looking at this relationship here, we have x prime is equal to a1 times, actually I'm going to factor an a1 out. So I'm left with x plus a2 over a1 times time. I know what a2 over a1 equals, so this is equal to a1 times x minus vt. So the transformation between the two reference frames is equal to x minus vt times some constant here. If I now plug into this right here, I know that I have a1 x minus vt squared minus c squared times t prime squared, and that's t prime right there. So b1x plus b2t squared is equal to 0. So we have this whole mess right here. So I get a1 squared times x minus vt squared minus c squared times that whole mess there. Equals 0, and so I have a1 squared x squared minus 2xvt plus v squared t squared minus c squared times b1 squared x squared plus 2b1 b2 xt plus b2 squared t squared equals 0. This is just squaring a binomial, so a plus b squared is equal to a squared plus 2ab plus b squared. Or if it's negative there, then it's a negative here. So that's why that negative transferred there, and that stayed positive. Sorry, if I distribute, I get a1 squared x squared minus 2a1 xvt plus a1, that should be a1 squared, plus a1 squared v squared t squared minus c squared b1 squared x squared minus 2c squared b1 b2 xt plus minus c squared b2 squared t squared. And that whole thing is equal to 0. I want to get the squared terms together, so I have a squared term here. I have a squared term there, the x squared terms. So I get a1 squared minus c squared b1 squared x squared. Now let's get the x terms together. So I have an x term there, I have an x term there. Actually, let's do it in terms of x and t. So I have an xt there, and xt there. Minus 2a1 squared v plus 2c squared b1 b2 times xt, and then plus, and now I have my t squared terms over here. I have a1 squared v squared minus c squared b2 squared t squared equals 0. And yes, I do recognize this looks like a mess at the moment, but it will clean up in just a second. That should be equal to x squared minus c squared t squared because of the invariant. Remember, this comes from the x prime squared minus ct prime squared. So if this is true, no matter what the value of x and t are, that means that, because I have an implied 1 right here, this means that a1 squared minus c squared b1 squared equals 1. This whole thing right here, since there is no xt term here, this whole thing here has to equal 0. So I have 2a1 squared v plus 2c squared b1 b2 equals 0. And this term right here has to be equal to negative c squared. a1 squared v squared minus c squared b2 squared equals negative c squared. From this equation here, we have b1 squared is equal to a1 squared. So basically bring this over here, that over there, and then getting rid of that coefficient. a1 squared minus 1 over c squared. From this equation here, we solve for b2 squared. So b2 squared equals, bringing this over, and then divided by negative c. Actually, probably easier to bring that over this side, this over to that side. So I get a1 squared v squared plus c squared divided by c squared, which is a1 squared v squared over c squared plus 1. And then from this equation here, we have 2c squared b1 b2 equals negative 2v a1 squared. If we square both sides, we get 4c to the fourth b1 squared b2 squared equals 4v squared a1 to the fourth. We have a formula here for b1 squared. We have a formula here for b2 squared, so we'll plug those in. So I have 4. Actually, the 4's cancel out, so good on us. So I have c squared times a1 squared minus 1 over c squared. C to the fourth. That's b1 squared. b2 squared is a1 squared v squared over c squared plus 1. And that's equal to v squared a1 to the fourth. So distribute, we have that c squared cancels out with 2 of those. Then we'll distribute that over here. So I'm left with a1 squared minus 1 times a1 squared v squared plus c squared, when we distribute that c squared over here, is equal to v squared a1 to the fourth. And the tension is mounting. If we multiply this out, I have a1, so foiling, so a1 to the fourth v squared plus a1 squared c squared minus a1 squared v squared minus c squared equals v squared a1 to the fourth. Let's solve for a1, because remember a1 is the coefficient. Let's bring that out. a1 is the coefficient for this Lorentz transformation right here. And solving for a1, so I have this right here. I want to solve for a1. And so those cancel out. And let's bring the c squared over. So I have a1 squared c squared minus a1 squared v squared equals c squared. a1 squared times c squared minus v squared equals c squared, and a1 squared is equal to c squared over c squared minus v squared. Putting that in a more traditional form, we'll multiply top and bottom by 1 over c squared. And I'm left with 1 over 1 minus v squared over c squared. Therefore, a1 is equal to the square root of 1 over 1 minus v squared over c squared, which, if you recall, is gamma. So our first Lorentz transformation, we had x prime is equal to a1 x minus vt, and we now have a1 is equal to gamma, the Lorentz transformation factor. I know that b1 squared is equal to a1 squared minus 1 over c squared, which is equal to gamma squared minus 1 over c squared, which is equal to, well, I know that from the previous page, gamma squared is equal to c squared over c squared minus v squared, because a1 is gamma, so gamma squared, that should be an a1, is equal to that, or that, whatever form you want it in. This is the form I want for right now. So this becomes c squared over c squared minus v squared minus 1 over c squared. Getting common denominator to do the top here, the numerator, so I have c squared over c squared minus v squared minus c squared minus v squared over c squared minus v squared, all over c squared, which is, when I combine them, the c squares will cancel out, and I'm left with v squared over c squared minus v squared over c squared. Which would be, so So dividing by that, same as multiplying by the reciprocal, so I'm left with v squared over c to the fourth minus c squared v squared. So that's b1 squared. b2 squared is equal to a1 squared v squared over c squared plus 1, which is gamma squared v squared over c squared plus 1, which is c squared over c squared minus v squared put the parentheses there, v squared over c squared plus 1, which is, well, the c squareds cancel out, and I'm left with v squared over c squared minus v squared plus 1, which is v squared over c squared minus v squared plus c squared minus v squared over c squared minus v squared. Combining them, the v's cancel out, and I'm left with c squared over c squared minus v squared. So recognize that this is just gamma squared. This is what we did on the previous page. I'm going to flash that in front of you just now. We had a1 squared was equal to c squared over c squared minus v squared. So that's just what we figured out, gamma squared. If I multiply times c to the fourth over v squared times b1 squared, I get, well, the v squared is going to cancel out there. The c to the fourth, so I'll end up with c to the fourth over c to the fourth minus c squared v squared. I can factor out a c squared and cancel out, so I'm left with c squared over c squared minus v squared, which is just gamma squared. So therefore, b1 squared equals, multiplying, getting that over to the other side, v squared over c to the fourth times gamma squared. Therefore, going back to our transformation, I know that t prime is equal to b1x plus b2t. So that's equal to, well, this is a b1 and that's a b1 squared, so it's going to be plus or minus v squared over, v over c squared gamma plus or minus gamma t, which is gamma v, x, which is gamma v over c squared x plus or minus t. So is it positive or negative? That's the part that we now have to figure out. So recognize that if the speed is small, that we should still get, basically Galilean relativity still holds. We have t prime is equal to gamma plus or minus v over c squared x plus or minus t. All right, so we're back. If v is much less than c, so much less than c, in other words, v over c is practically 0, Galilean relativity must go into effect. Is good enough. So first off, time in Galilean relativity, time does not change. We're traveling at slow speeds here. And so therefore, if v is close to c, that means that gamma is approximately equal to 1. This term right here drops out, and so what I'm left with is t prime is equal to t. This has to be the positive solution. But what about this one right here? Remember where this comes from. We have b1 is equal to plus or minus v over c squared gamma. We've established now b2 is equal to gamma. We know that a1 equals gamma. Now, when we did our derivation earlier, we had this relationship right here. I'm going to rewrite that equation. So we have 2a1 squared v plus 2c squared b1 b2 equals 0. I know gamma is always a positive number. It's 1 or bigger. So this is positive. V is a positive number. Presumably, we had it going away at some speed in the positive direction. So that's positive. That's positive because that's also gamma. That's the speed of light. That's positive. So in order for this equation to work out, B1 must be negative. So the negative solution works there. And so what we end up with is then T prime is equal to gamma negative V over C squared X plus T, or more traditionally, gamma times T minus V over C squared X. And then we have X prime, just rehashing that one, is X minus VT. And those are the Lorentz transformations. If we went from the other point of view, because this was, we had some S here and S prime is moving at some speed V with respect to S. If we flipped it around, S prime is this way, and from S prime's point of view, S is traveling this way at a velocity of negative V, and so X is equal to gamma X prime plus VT prime, and T is equal to gamma T prime plus V over C squared X prime, going in the other direction. So those are the derivation of the Lorentz transformations. I know that was just nonstop thrill ride excitement. And so therefore, what comes next is actually using this. So I'll probably make a short video with just the Lorentz transformations, just so you can bypass the derivations. And this is for those who are curious.